instead we put this bar on top. So remember, all that you do, you just take the real part, which in this case, sorry, the imaginary part, and you basically multiply it by -1. So just showing you using these examples, here in the first example, I want to figure out the conjugate of 2 plus 3i, right? Now the imaginary part is 3, so I just multiply that by -1, I get -3. So I get 2 minus 3i. In the second example, I got -1 minus I. So with the imaginary part, if I just change the sign, it comes -1 plus I. And that's really all it is. So taking the conjugate is a fairly straightforward operation. Now in terms of what does this look like visually, okay, so let me just draw it for you. Okay, so let's say you have 2 plus 3i. So let's say this is, again, this is the real axis. So it's better to write it like this, RE, short for real, IM, short for imaginary, okay. So 2 plus 3i, so let's say 3i is here. So this point would correspond to 2 plus 3i, right? And in fact, the way that I've drawn it, I might run out of space here. Let me extend this down. Okay, so this is not exactly the scale. Sorry about my bad drawing. But if you want to see where the conjugate 2 minus 3i would be, right? So let's say minus 3i is here, then this is where 2 minus 3i would be. So this is where the conjugate of 2 plus 3i would be. So you can see when you take the conjugate of something, right, really what you're doing is you're reflecting it about the horizontal axis. So that's what conjugation corresponds to visually. You just take your complex number and you reflect it around the horizontal axis. So in fact, in the example of the second one, we had -1 minus I. So let's say -1 is here, and let's say -I is here. So this point would correspond to -1 minus I. Now remember, the conjugate was -1 plus I, which would correspond to here, right? This is -1 plus I, or the conjugate of -1 minus I. But again, you can see what's happening is I'm just, oops, that was supposed to be a straight line, sorry, but I'm just reflecting it about the horizontal axis. And that's really all it is, just to give you a visual idea. Okay, here are some properties of the conjugate, right? Some of these are quite straightforward. So the first one is saying that if you take a complex number and if you apply the conjugate to it twice, you get back to the same complex number. So I think that one's fairly straightforward to see why that's true. So let's say the complex number z is x plus iy, right? Kind of the standard convention. If I take the conjugate twice, so if I take the conjugate one time, I get x minus iy, right? And then if I take the conjugate again, I get x plus iy. So obviously I go back to where I started from. Alright, the second point is saying that when you're adding or subtracting, or even multiplying, and dividing is not there, but it should be, it doesn't matter if you change the order of the operation and the conjugation. So in other words, you can add and then take the conjugate, or you can take the conjugate and then add. Or you can multiply, take the conjugate, or you can take the conjugate and then multiply. That's really what the second property is saying. It's a good exercise to try and prove these on your own, because it'll help you to understand the idea of conjugate a bit better. Maybe I'll prove this one for you, right? Just to give you an idea of how you would set out your work. So I want to prove that if z and w are complex numbers, and if I take their conjugate, that's the same as taking the conjugate of z and multiplying it by the conjugate of w. So in order to prove this, we just let z and w be two random complex numbers. So I can let z, for example, to be a plus bi, and let w to be c plus di. Right? Two arbitrary complex numbers. Then what I get when I multiply z and w and take the conjugate, right? So z times w is going to be a plus bi times c plus di, taking the conjugate of that. Now if I expand the brackets out, I'm going to get AC, actually I don't really need the bracket, I don't know why that's there. I get AC plus ADI plus BCI plus BDI squared, or conjugate. And remember, I squared was -1, so really this comes out to just be AC minus BD. And if you take out a common factor of I, you got the AD plus BC. And you want the conjugate of this. And remember, what do we do when we take the conjugate? We just reverse the imaginary part. So currently it's plus, I make it a minus. So I get AC minus BD minus I times AD plus BC, right? And think about what would happen if we did conjugate of Z times conjugate of W. So if I did that, well, the conjugate of Z is A minus BI, and the conjugate of W is C minus DI. And when I multiply these together, I get AC minus ADI minus BCI. I get plus BDI squared, but I know I squared is -1. It becomes minus BD. And so I can write this like this. Right? And you notice that this is the exact same as this. Or in other words, this is the exact same as this, which is what I was trying to prove. So you can see the proof is fairly straightforward, but that was just to give you an idea of how to set out your work. So it's a good exercise to try and prove the other property as well. Now the third bullet point here, so this is saying that when you take a complex number and you add its conjugate to it, you get 2 times the real part. So that's quite an important one. So to see why that's true, so let's say for example z is some random complex number a plus bi, right? If I do z plus z conjugate, I'm going to get a plus bi plus the conjugate of z, which is a minus bi. And so what happens, the bi's cancel, I'm left with 2a. But notice that a is the real part, so it's 2 times the real part of z. So it's fairly easy to see why it's true, and hopefully you can easily see why the other bit is true as well. That if you subtract the conjugate, you get 2 times the imaginary part. And you can also easily understand why this is true visually. So for instance, let's say I have a complex number z here. As we mentioned, when you take the conjugate, it's like reflecting about the horizontal axis. So z conjugate could be down here. And the thing you should know about adding complex numbers, it works exactly like vector addition. So if I want to see where is z plus z conjugate, it's like adding this vector to this vector. And in case you're not familiar with vector addition, basically the idea is you can kind of move it. So this would come here, this would come here, right? So this would be the sum, z plus z conjugate. And as you can see, it's a purely real number. So that's an easy way to see why it holds visually. But in any case, these properties are quite important to remember as you use them quite a bit. So it's a good idea to try and prove it on your own as well. It will help you to remember actually. Let's have a look at an example just to help us understand these properties. So this example that I have here, we're given that we have 2 complex numbers, z and w, and at the moment they're unknown, so we want to find them. And the information that we're given is that when you add them, you get 8 minus I, and when you subtract their conjugates, you get -10 minus 5i. And we want to figure out what z and w should be using those properties. Okay, so let's start here. So we know that conjugate of z minus conjugate of w is minus 10 minus 5i. Now, this is the same as saying the conjugate of z minus w is minus 10 minus 5i, right? Because remember what we said on the previous page. We said that you can subtract and then take the conjugate, or you can take the conjugate and then subtract, right? It doesn't matter. So we know that this is true. Now if I take the conjugate of both sides, well, on the left that would give me a double conjugate, which remember cancels out. And the conjugate of the right would be minus 10 plus 5i. So what I have right now, I know that z minus w is minus 10 minus 5i, plus 5i, sorry. We're given z plus w is 8 minus I. And now, as you can see, I got two equations with two unknowns. So I can solve this simultaneously fairly easily, right? So I've called these equations 1 and 2. So if I add equations 1 and 2, so 1 plus 2, well, what's going to happen is the w's are going to cancel. So I'm going to get 2z. And then if you add the right-hand sides, again, it's just about collecting like terms. So minus 10 plus 8 is minus 2. 5i minus I is plus 4i. And so therefore, dividing both sides by 2, you get your z. So minus 1 plus 2i. And now that I have z, I can easily solve for w. So I can substitute it back into either equation 1 or equation 2, it doesn't matter. So let's say substitute it back into equation 1. So hence equation 1 becomes, so I got minus 1 plus 2i, which is z, minus w, was minus 10 plus 5i. So taking the w to the other side and bringing the minus 10 plus 5i to the left side, get minus 1 plus 2i plus 10 minus 5i equals w. And again, collecting like terms, I get 9 minus 3i. And so that's my solution. So that's my w, and that's my z. And that's the idea there. So yeah, hopefully that gives you a better bit of an idea of how conjugation works.